Hi, this is OrgoChemSimplified, and today we're going to do a problem in carbonyl chemistry. It's a fairly simple problem. We have this compound here, which is an ester, and we're reacting it with ammonia, and we're asked what the product is. So whenever you have a problem like this, it's a good thing to work out the mechanism. It doesn't have to be on paper. If you're comfortable enough, you can do it in your head, but you want to be able to work out the mechanism and understand where you get the answer from, not just guess it. Okay, so whenever you have a reaction, the first thing you want to ask yourself is, how are these two molecules going to interact in the first place? I don't have to get the product right away, I just need to know how these two compounds will interact. Well, let's see. We know nitrogen, NH3, when it has 3 atoms bonded to it, it has a lone pair. What else do we know about nitrogen with lone pairs? They're very good nucleophiles. So this is probably going to act as a nucleophile. That's how we've seen it act before. And because this is going to act as a nucleophile, this compound is going to be the electrophile. Right? The ester is going to be the electrophile. And what's the most electrophilic atom? Well, in carbonyl chemistry, we know this O is more electronegative. It pulls some of these electrons from that carbon, so this carbon is going to be positive. It's going to want those electrons. So the carbon is going to be the most electrophilic atom, the carbonyl carbon. Okay, so we know this lone pair is going to attack the carbonyl carbon. Now we know oxygen is going to want to pull a pair of electrons towards itself. And we know that because, first of all, you can't have 5 bonds to carbon, but second of all, it's more electronegative. And when we do this, we'll get a tetrahedral intermediate. Right. So we'll try to preserve the same shape. Okay, so now we have this compound. We have a tetrahedral intermediate with an oxygen that's negative, and we have an NH3 plus here. Okay, so the first thing we want to do is get rid of that positive charge. And the reason for that is that, we have a basic solution. The solution is mostly NH3. So positive charges in basic solution aren't going to exist for very long. So we'll just take the most basic thing we have in the solution, which is another ammonia. It's going to take its lone pair and grab off that proton. Okay? And when that happens, that leaves us with this compound right here. Okay? So that NH2 is stable, right? So the next logical step is, whenever we've seen the tetrahedral intermediate with carbonyl chemistry, we know that the negative charge will come down, it will collapse on itself to reform the carbonyl. And the reason that happens is because the carbonyl is more stable than the tetrahedral intermediate. So it's going to want to collapse these electrons and reform that double bond. And in order to preserve those 4 bonds to carbon, one of these bonds have to break, right? So we're left with a choice between the breaking of the NH2 bond, the breaking of a carbon bond, and the breaking of an oxygen bond, a CO bond, right? Well, let's see. If we break the CNH2 bond, we're just going backwards, and we're going to go back to this to our starting material, right? That's not going to progress ourselves forward with this reaction, right? And carbon-carbon bonds, they don't break because they're very stable. Carbon-carbon bonds are the most stable because of the fact that their energy levels are very close. And so the electrons are shared equally, it's very stable. The greatest difference in electronegativity and the lowest pKa-H, that's usually how you go about choosing which one is going to leave. The one with the lowest pKa-H, the one that's the most stable. Okay? So we know this negative charge is going to collapse down, and the only logical choice to kick out is the oxygen. So that's going to open the ring. Okay? So let's count carbons, right? 1, 2, 3, 4, 5 carbons, including the carbonyl carbon. So I'm going to draw this carbonyl carbon here with the NH2. And we know there's 5 carbons, so 1, 2, 3, 4, 5. And then the O minus. So whenever you have a ring structure and you're opening it, you want to count carbons so you don't screw up how many carbons there are. Okay, so finally, the only thing we have left to do with this compound is protonate it to make it a neutral compound. And we had this NH3 take off a proton earlier, so now we have an ammonium ion. And that's the most acidic compound. So it's going to grab that proton and give us our product. So our product is this neutral compound. So when we write down our final answer, I'm just going to copy it up here. And that's your product. So again, whenever you have a mechanism problem, just see how you start, figure out how they're going to interact in the first place, and then all you have to do is follow the steps, figure out your mechanism rules, see if each of these steps make sense, and see if there's a better alternative. And if there isn't, you're on the right track. And you just keep moving forward until you get your final answer. And that's going to give you your product. So hopefully that helped in terms of figuring out how to think about one of these types of problems. Just use the characteristics of each of the compounds. So if you liked the video, please click thumbs up. If you have a question or comment, leave it below. I'll try to get back to you as fast as I can. And thanks for watching.